In this video, we're going to define cardiac output using integration. And somebody can explain this much better than I can, so I will defer for the most part to a video here that I'm going to show you that explains it pretty well. But roughly what we're talking about here is we're going to think about the total volume of blood that's pumped out of the heart. So the typical flow of blood through the heart, it'll come through the pulmonary veins into the right atrium. This is blood that's in need of oxygenation. That'll go pass into the lungs, get oxygenated, and then back into the heart into the left atrium, which then sorts it out through the aorta into the rest of the body. Now, in theory, blood in is blood out. So there's no loss of blood here through this closed system. And if we want to measure how much comes in any given period of time, what we do instead is we inject, or well, I say we, but the actual specialists who are measuring cardiac output would inject a dye into the right atrium. And a certain amount of dye is injected, and its concentration in the blood is measured in equal intervals of time until the dye has cleared. And so roughly what we want to think about is if a cardiac output is the total volume of blood. Oops, that's not how you spell blood. In and out of the heart. Then what we're really talking about is flux through the heart. And so the way that the dye is helpful is that this flux is measured as a proportion where we are looking at the concentration of the dye as a function of time, and we're going to measure it the integral up until the time that the dye clears, and divide the total amount of dye by that integral. And this should equal the flux because the flux is constant. And we just have to wait until the dye clears to perform this. And so when we measure the concentration of dye, there's typically some special equipment that is measuring the dye through a given piece of the heart, typically in the latter sequence of the process here. And so let me actually link that video now. That is helpful in explaining that.
The heart is a pump at the center of the human circulatory system. It beats tirelessly, moving blood through a network of veins and arteries and delivering oxygen and nutrients to tissues and organs throughout the body. The circulatory system also returns blood from the body to the lungs, where it can get a fresh supply of oxygen. The right side of the heart is on the left side of the screen, and vice versa, because the patient is facing you in this graphic. Blood that needs a fresh supply of oxygen arrives to the right side of the heart via the inferior vena cava and the superior vena cava, the body's largest veins. As the heart beats, that blood gets pumped through the right atrium and ventricle and into the pulmonary artery, which leads to the lungs. The pulmonary artery is the big blood vessel that connects the heart to the lungs. Emerging from the right ventricle, it splits into two branches, one leading to each lung. These branches continue to branch into smaller and smaller vessels, which allow oxygen to more easily enter the blood in the lungs. The right side of the heart is in charge of pumping the blue, deoxygenated blood to the lungs, where it flows into very tiny vessels that allow the blood to absorb oxygen from the air we breathe. That blood becomes oxygenated, which we show as red, and travels back to the left side of the heart to get pumped out to the body. Red blood returning from the lungs pours into the left atrium. From there, it flows into the left ventricle and then into the aorta, the body's largest artery. The aorta brings red oxygenated blood up to the head and arms and down to the abdomen and legs. In a healthy heart, the left and right sides work in unison. As the heart beats, it pumps blue blood to the lungs to get more oxygen and red blood out to the body to bring oxygen to the tissues. These two loops of the circulatory system are separated, which helps the heart move blood very efficiently.
Right, so that's the explanation. That's much better than my personal explanation. But as you can see, it's a closed system. The point here is that when we define cardiac output in terms of integration, we're able to use the concentration of the dye in the blood to help us figure out what the total output is. And so the missing pieces here are, of course, how much dye is ejected, the concentration function, which is a decreasing function, of course, and then the time until the dye clears, which can be measured using equipment.